And remember that when this origin here coincides with this origin, that's when, well, that's when the clocks are synchronized to be, they both read the same thing, 0, 0. And that's this, and that happens when we have that. What happens if this clock, like this person, maybe this person has a watch. Well, there's a watch to be here, right? Or clock. What's the space coordinate of that clock? X prime is, if I wrote, it would be 0, 0, 0, right? Point is that X prime is 0, right? Because it's at the origin, right? For that coordinate, right? So suppose that this clock is ticking. Dun, 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 and it's periodic, right? And between ticks, for example, the time is t prime. Okay, like delta t, if you like. Like, let's say delta t prime is like a period. I'll call it t prime. And actually, there's for the moment, I'll call it that, right? Now, as this clock is going to and moving this way, right? Us, in this frame of reference, we see like this thing going, right? Well, it will be going very fast for us to notice the effect, but it goes fast. To us, what does our clock say? How fast is our clock in our origin ticking, right? So all I need to do is take this expression here, and I can say, well, our time, right, will be gamma t prime minus or plus x prime over c squared, right? But the clock in this person, right, is 0. And I can say that the time interval between ticks, as measured by us, is equal to gamma times the time interval as measured by the other person, right? So we have this. And let's put in the value of gamma, right? So this will be delta t prime, well, which is t, well, I guess I don't need this over here. And then this would be the square root of 1 minus u squared over c squared. Again, if u is very small compared to c, if the speed of this frame of reference is small compared to the speed of light, then you neglect that. 1 minus 0 is 1, square root of 1 is 1, and then they tick at the same rate. Right? But if u is big, then you can't ignore it. Then what we have is this. Let me define something. Notice that in this problem, right, to us, right, this clock is, to us, we were keeping track of 2 clocks. To this person, right? To this person, right, this is the reading of this clock, this one. So to that person, imagine I'm in this spaceship going fast. So I'm traveling this way, right? I'm in a spaceship. I said, oh, hi people at OCC, and then I'm going this way, right? So to me, my clock is in the spaceship, is at the origin. And I keep going, and it's at the origin. And I keep going, and it's at the same place in space, to me, right? Same place. Now to us, as we watch this person go by, right? Let's say it was here, when the chair was here, it ticks over there, and then it ticks again over there. So to us, the ticking of time didn't happen at the same place in space. It ticked over here, and then later on it ticked over there, because it's moving relative to us. But to that person, right, it's like I'm traveling with it, and the clock is with me, moving with me. So in that frame of reference, that the clock is in, the ticking of time, right? The events, the time interval between the two events, those two events in that frame of reference happen at the same space. X prime, Y prime, Z prime being 0. Whatever it is, I just chose 0. Right? But to us, that's one event, one tick. The next tick is over there. The next tick is going to be over there. To us, that's happening in different locations. So the time interval between the two events that happen in the same space for that frame of reference is called the proper time. So in the moving clock, right, it's like there's the clock, it's taking same spot in that frame of reference. So this is called the proper time. And people tend to call it like delta T0. What's the notation that we used? We used delta T0. So that's just the proper time. Let me give you another example. I'm in an airplane, right? And I'm in the airplane, and I'm sitting in the airplane, and I'm flying. And you guys are there in the room when I'm in an airplane. And as I fly this way, I go. So what are the two events? I throw the keys, and I catch the keys. I throw the keys, and I catch the keys. So to me, let's say the two events are, the time interval that I'm going to measure is how long are the keys are in the air. For how long are the keys in the air? So I'm in the plane, and I go like, they were in the air for half a second. So to me, in my frame of reference in the airplane, the beginning of the first time interval was here, in front of my chest, right? That's when they left my hands. And the second event is when I catch them, but I catch them at the same spot. So to me, it's like, I'm measuring the time interval between an event that happened here and the second event happened there. Because when I caught them there again. So let's say I throw them here and I catch them at the same spot. So I measure the proper time. Because to me, the two events happen at the same space. In my space, it was the same space. It's the same X coordinate, the same Y coordinate, the same Z coordinate for me. But for you, watching it from over there, when I'm moving this way, right? And when I throw the keys, I'm here, right? But then I catch them. To you, you say, he threw the keys when he was there, but he caught them when he was there. So those are two different points in space. You do not measure the proper time. Now, which of these two is longer? If I write this, notice, U is going to be less than C, but I'm going very fast. Let's say 90% the speed of light. So U is going to be less than C. So I take 1 minus that number. It would be a number less than 1, but positive, right? And the square root of that is going to be a number less than 1. And if I divide by a number less than 1, I get something big times delta T prime times the proper time, or something big times delta T0, the proper time. So in other words, the time interval that you measure on the ground is longer than the time interval that I measure on the plane or in the spaceship. So, right? So what I did is this. It's kind of cute. What I did is this. Let's think about this in a certain way. Let's think about this equation. Let's play with some numbers. Let's see what it says. There it is. Okay. So, suppose that I'm in the spaceship, an airplane, and I throw the keys up, and I catch them, and that was 1 second. Now, this is an airplane. You're over there, as I fly this way. How long do you say the keys were in the air for? Then you say, well, he was only going at 500-600 miles an hour. That's small compared to the speed of light. So this is small. So you measure this. You measure delta T, right, in that frame, and I measure the to me, the keys are in the air. 1 second, 1 second. I'm gonna throw them, I'm gonna be considering what happens if I travel at different speeds. So if I travel at some speed, like in an airplane, 500, 600 miles an hour, the keys are in the air to me for 1 second, right? What would it be to you? To you, you would say, well, I should really use this, right? But 500 miles an hour is small compared to the speed of light. So when I take this ratio, it's going to be very small, and on top of that, I square it, it's even smaller, so forget about that. So I just have 1 minus 0, square root of 1 is 1, so then the time that you measure on the ground is the same as the time that I measure, which is 1 second. No problem, right? 2 events, throwing and catching. 1 second to me, 1 second to you. Fine. Now, what if I travel at half the speed of light? Now I'm in a spaceship that doesn't exist yet. Maybe in a few hundred years. So I'm not going to be on that spaceship because I'm not going to be around. I don't know about you, but I'm not going to be around. And I'm in the spaceship of the far future, say, or maybe near future, who knows, right? And I throw the keys, and they are in the air for 1 second. To me, right? 1 second. Now, if I travel at half the speed of light, for how long were the keys in the air? When you measure it left them, you say, oh, boom, caught. So that you would say, if you plug in 1 minus, and then for you, that would be 0.5. You over C would be 0.5. 0.5 squared is 0.25, so 1 minus 0.25 is 0.75. Take the square root of that, and then 1 second divided by the square root of 0.75, you get 1.15 seconds. So you say, those keys were not in the air for 1 second. You would say, those keys were in the air for 1.15 seconds. Now we begin to disagree. I said, come on, man, they were in the air for 1 second. I said, no, you're wrong. They were in the air for 1.15 seconds. What if I travel at 87% of the speed of light? And I throw the keys in the rocket, and they're in the air for 1 second. And then you measure it, right? You see me, I'm going at 87% the speed of light, and I throw them, and my clock says 1 second. Now you put in the numbers in here, right? U over C would be 0.87, 0.87 squared, whatever you get, 1 minus that, whatever you get, square root of that, boom, 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 you get 2 seconds. So to you, the keys were 1, 2, that was 2 seconds. To me, boom, boom, 1 second. What if I travel in a spaceship that goes at 99.5% of the speed of light? And by the way, protons at the Large Hadron Collider outside Geneva, the European Center for Nuclear Research, they accelerate protons to 99.99999969% the speed of light. But those are protons, not a spaceship, but someone can get on, right? And that requires a lot of energy. So imagine a spaceship, well, anyway. So I'm traveling at 99.5% of the speed of light, and I throw the keys up, boom, boom, 1 second. How long passes by in your life? 10 seconds. So you watch the keys, like I throw the keys, I'm in my chair, and I go, boom, boom, that was 1 second. You can say, hold on. You're gonna say, no, you threw the keys, and that was 1, 2, 3, 4, 5, 6, 7, 8, 9, boom, I caught them. So 10 seconds would go by, according to you. And then you would argue, man, you in that spaceship, your clock is running slow. Because it only says 1 second when it should be 10 seconds. So that's why the statement, clocks run slower the faster they move in space. And this has some interesting consequences, if I could call it that. If a spaceship where I could travel at 99.5% the speed of light, exists where I can get on it and travel at that speed. This means that in principle, you could be older than your parents. A scary thought, maybe. Maybe. Let me tell you why. So here's the Earth. And here you are. How old are you? Let's say 20 years old. Plus or minus, whatever. And here's your parent. Let's say your dad. let's suppose, your dad. And your dad is, let's say, 40 years old. And then your dad is watching the news, and then, breaking news. A new spaceship has been invented that can travel at 99.5% the speed of light. And we're looking for someone brave enough to go on a trip with this spaceship. And your dad said, yeah, I want to go. And he gets chosen. And he goes in this trip and comes back. And he's gone for 1 year. So, he gets in the spaceship and he's gone, 365 days, he's a year older. How old is he when he comes back? Travels at 99.5% of the speed of light, right? So how old is he when he comes back? 41 years old, because 1 year went by. But how old are you going to be? 30. You're going to be 30 years old. And then he says, oh, gee, my goodness, I forgot my iPhone. I got to go get it. So the next day, then he gets back on this spaceship, and it goes, makes this trip, right? And another year goes by. So when he comes back, he's 42 years old. But us on Earth, 10 years went by. So now we are, or not me, I wish. Now you're 40 years old when he comes back. And then he says, oh, sorry, son, I forgot your mother over there. I gotta go get her. Otherwise, I'm in big trouble. And then, then he makes another trip, and then he goes back, comes back, he's gone for a year, he comes back, and he's 43 years old. But 10 years went by, now you're 50 years old, and now you're older than your father. This formula, right, has been around since 1905. And it's been tested again and again and again in various situations and so on. And it has never failed a test. Never. And there are people who want it to fail because if I prove that that's wrong, I'm going to win the Nobel Prize in Physics next year or so. Right? It hasn't been proven wrong. Experimentally, in the experiments that could be done and so on. Like in the 1970s, when I said that was tested, or confirmed experimentally, they, set up these atomic clocks, which are very, very, very precise, and they flew them around the world in different planes, and then they took into account, the speed of the earth, the planes and so on. And okay, let's not throw away all of these terms. Let's really keep them. The U/c squared. Let's keep it in there, right? Many decimal places, and then, by how much should they be off by the time they come back? And they were off by the amount that's predicted by this theory. The GPS system, again, if it wasn't for this equation, it wouldn't work. That would be a technology that we wouldn't enjoy using. So, you tell someone this and you tell them, yeah, you could in principle be older than your dad. And you're like, what you're crazy, come on, man, do something other than physics. Is what someone might want to say to you, because it is really crazy, right? I mean, how could you be older than your parents? So, I mean, it really sounds crazy. But mainly because, we've never met anyone who's older than their parents, right? Right? It's just, we've never experienced this time dilation effects. But the reason being is because we've never really moved on some rocket, some spaceship at speeds that are this big. I mean, the speed of light is 7.5 times around the Earth in 1 second, right? So imagine being gone for a year. So, the difference in the time that we would keep, it's at that speed, it's 1 to 10. 1 second to 10 seconds, 1 year to 10 years. You could argue that, therefore, you could travel into the future. Not backwards in time, but you can travel forwards in the future. Because what if your dad, for example, let's say your dad left in, tomorrow, so 2022. So when he comes back, he thinks on Earth it's 2023. Because in his clock, only 1 year went by. And by the way, biologically, he aged only 1 year. To him, it's normal. It's like I'm here. I'm just gone for a year. right? Now I go to bed tonight, and so everything is normal. I was just gone for the year. But when he comes back, well, the year really is not going to be 2023. 10 years go by. When he comes back on Earth, it's 2032. So it's like he really went into the future, into our future, not his future, but our future on the ground, right? So it's like, okay, I want to know what things look like on the Earth in the year 2000. Let's see, this would be when he took the trip again. That would be another 10 years. So he comes back 2042. He goes again 2052, right? So he says, okay, I want to know what life is like in 30 years from now. But I don't want to see people fighting wars and hating each other and so on. So I want to skip all that crap. I want to come back in 30 years. Well, get on a spaceship, just make the trip. It'll take you 3 years, but then when you come back, if you go at that speed, you'll come back and 30 years have gone by. That's like traveling into the future, right? And you're not gonna be able to travel backwards in time, but you can travel into someone else's future, right? So to him, he was gone for a year, period. It's not like 10 years went by for him. It's not like he aged 10 years, but he's gonna be 43 years old when he comes back. But 30 years went by on Earth. So in that sense, you can travel into someone else's future, I guess, if we want to call it that, like that. So, weird effects. Albert Einstein, just to finish, Albert Einstein wrote this theory in 1905, and he started talking about this, and it's like, he actually met a lot of opposition, and a lot of people, I guess he was never awarded the Nobel Prize in Physics, and you can wonder why. I mean, maybe it was too advanced of a theory for people to comprehend. But then again, the ultimate test of any theory is experiment. And a lot of his predictions based on this theory were just confirmed experimentally after he died, with more advanced technologies. I mean, we don't even have this technology to make something today, to make something travel that fast so that then you could test it, let's see if my dad is really, if I'm older than my dad, But so he never, So the math that I've used on the board is, it's really high school math to some effect, to some sense, But the physics is like very counterintuitive. It's alien to us, like. But anyway, so I've actually covered. I wrote a lot over there. So if you look at these notes over here, just to finish. So I started with the postulates, and then I talked about the Galilean transformation equations, which are this. Right? We showed what those are, asked some questions, took some differentials, and then I derived the Galilean transformation equations for velocities. This is like the truck baseball equation. But then what about simultaneity, right? And anyway, this is similar to the argument of the light bulb being turned on in the middle of the room and someone watches from outside. And then this is another way to derive the time dilation equation. But it's easier with the other argument that I used. This is gamma. There's something else called length contraction. And anyway, there's another way to also derive that expression that I discussed over there. Then there's something called length contraction, which I didn't say anything about today. I'll say something about it next time. And length contraction. And then these are the Lorentz transformation equations. Notice this is already page 16, but I just wrote them down. And then you get the velocity transformation equations, the correct ones, the more general ones. And then we start to talk about linear momentum. So with this modifications, the expression for linear momentum is not just mv, it becomes something else. The expression for kinetic energy, let's see if I have it over here. Yeah, the expression for kinetic energy is not 1/2 mv squared anymore. If the object is moving close to the speed of light, it's a different expression. It's gonna be, I'll show you where this comes from. Right? So, and other phenomena like that. What else? And then I'll talk about relativistic energy equals mc squared. And this is amazing here, pair production. So one of the messages, I think we're never gonna finish this, right? So E equals mc squared, right? So the argument there is that matter and energy are like two manifestations of the same thing. So that means that energy can be converted to matter, and matter can get converted to energy. So if I take these keys, right? If I take these keys, right? It's a metal, it's made up of atoms with nuclei and electrons going around. Those nuclei have electrons and protons. I'm sorry, neutrons and protons. And the protons and the neutrons themselves are made of smaller particles called quarks. So it's something made up of quarks and electrons. And the interactions, and so on. But what if I were to turn this key completely into energy? So that no more atoms, no more electrons, no more nuclei, no more protons, no more neutrons, no more quarks. Just convert it to pure energy.
Isn't that what a nuclear reaction is?
Right. So if I take this mass and I multiply by the speed of light squared, that'll tell me the energy content of this. If I were to convert this into energy, that's what I would get. In nuclear fission, what you do there is you have a nucleus of uranium,